So if you remember back to Monday, we were looking primarily at temperature. And with regard to temperature, we looked at the 3 different temperature scales. The Kelvin scale, which is the absolute scale, the one that is based on energy. And then we looked at the Celsius and the Fahrenheit scales, which are based primarily on definitions. The water boils at this temperature and freezes at this temperature. And I shared with you a pair of equations, well, really a trio of equations that allowed us to convert between these 3 scales. So the important thing to kind of pull away from this is that your Celsius scale and your Fahrenheit scale, we can interconvert between the 2. We just need to use the right equation at the right time. And again, the factor, the 1.8 here, in each case, comes from the fact that every degree on the Fahrenheit, or excuse me, every degree on the Celsius scale is 1.8 degrees on the Fahrenheit scale. Kiara, do you have a question?
The conversions you gave us on Monday
are they?
No, I just want to make sure I have the right ones, because I have for Celsius is 1.8 times F plus 32, and then for the Fahrenheit it was 3 minus 32 divided by 20.
Okay, I got those backwards on Monday. These are the correct ones, and I apologize for the error. Yeah, I got the 2 switched. Fahrenheit is off by 32 degrees. We can see that here on the scale. 32 or Fahrenheit is 32 degrees higher than Celsius on the 0 point of the scale, the freezing point. And if we take that 1.8 degrees per 1 degree Celsius, we would get that instead of 100 degrees between freezing and boiling, we get 180 degrees between freezing and boiling. And so that's where that 1.8 comes from. So thank you, Kiara. We don't want anybody getting the wrong answers on the quizzes. Kelvin is just a scalar from Celsius. We can see that Kelvin is 273 degrees off of the Celsius scale. And that is the only difference between them. A 100 degree difference in the Celsius is also a 100 degree difference in the Kelvin. They are the same scale, just offset by 273 degrees from each other. Now, where we're going to use this is we're going to do a conversion problem. Let's just say, for the sake of argument here, that the temperature of the coffee in the student union is 205.43 degrees Fahrenheit. First of all, if you're carrying around a thermometer in your pocket when you go to get coffee, people might start asking some questions about you. Second, if you were walking around with a thermometer in your pocket and you found that your coffee was 205 degrees, you would want to let that cool down and probably inform somebody because something's wrong. That is insanely hot coffee. Burn the crap out of your mouth coffee. That being said, what are the temperatures on the Celsius and Fahrenheit or in the Kelvin scales? This is where we've got to pull in our equations. So we want to go from Fahrenheit to Celsius. So if we're going 205.43 minus 32, and then divided by 1.8. Order of operations tells us to do the subtraction first. 205.43 minus 32 would give you 173.43. Now we take that and divide by 1.8. Our Celsius temperature is a robust 96.35 degrees Celsius. So again, and this should make sense. This is how we know that we did the problem right, that we used the right equation. The boiling point of water is 212 Fahrenheit, and we're near that point. We expect that we're going to be near the boiling point of water for Celsius, which is 100. And 96.35 is certainly close enough to that. So part one, ding, we got it done. Now we need to do the Kelvin. Kelvin is equal to Celsius plus 273. So we've got 96.35 degrees plus 273. This would give us 369.35 Kelvin. One thing to notice about this, Kelvin does not have a degree symbol associated with it. So unlike Fahrenheit and Celsius, where the unit is degrees Celsius, degrees Fahrenheit, we don't tend to say degrees Kelvin. We just say Kelvin. So the temperature here, 369.35 Kelvin. There's no degree symbol on it. Any questions about this practice problem? All right, so let's move on to an application of temperature. Again, temperature is a measure of hotness and coldness, but we've got a problem here. Doesn't do a whole lot for telling us much about energy other than this is the current energy of the system. Thing is, most of the time when we do chemical reactions or when we are looking at physical processes, temperature changes. And when we see energy transfer as a result of temperature changes and temperature differences, we call that energy heat. So heat energy is generally associated with any one of these three processes: a change in temperature, a change in phase, so solid to liquid, liquid to gas, gas to solid, whatever the case may be, or a change in chemical identity, meaning we've got some kind of chemical reaction that's occurring, and as that chemical reaction is occurring, heat is being transferred one way or the other. So heat energy, in general, is associated with one of these three processes: change in temperature, change in phase, or change in identity, chemical reaction. Now, 2 out of these 3 are physical changes. And we're pretty familiar with those two as well. Which direction does heat flow? Hot to cold. So this is where temperature comes in. We can use temperature as a measurement of that hotness and coldness to help us predict which direction the heat is going to go. Always goes from the hot object to the cold object. Never goes in the reverse direction. Now, when it comes to any of these processes, we can describe the heat transfer as either being endothermic or exothermic. An endothermic process is one where heat is coming into the object. So take, for example, an ice cube. As an ice cube melts, heat is going into the ice cube to help turn those solid molecules and get them to separate from each other enough to form a liquid. That's an endothermic process. But what's interesting about that process is that there is an exothermic process going on simultaneously. In that the air surrounding that ice cube is getting colder because the ice cube is taking the heat from the air. And this speaks to a familiar but needed to be stated explicitly concept. The law of conservation of energy. Law of conservation of energy says that in any process, energy is going to be neither created nor destroyed. So what that really means for us here is, if I'm looking at that ice cube sitting on the counter, for the perspective of the ice cube, it's an endothermic process. Heat is coming into the ice cube. From the perspective of the table and the air and everything around that ice cube, it's an exothermic process. All of the energy from those objects is being lost to the ice cube as the ice cube melts. If I look at the whole thing together, the end result is no net gain or loss of energy. All of the energy that was gained by the ice cube was lost by the surroundings around that ice cube. Net, no gain, no loss. So whether we call something an endothermic or exothermic process really depends upon what our frame of reference is. Now, ordinarily, we're thinking about the substance, the system under study. But understand that whatever is happening to that system, the opposite is happening around it. Our law of conservation of energy has to be followed in all cases. In terms of heat transfer, there are three primary modes of transfer: conduction, convection, and radiation. Conduction is the heat transfer that occurs when objects are touching each other directly. So you can think of things like you've got a metal pan on a stove, you turn on the stove, the electrical coils or the flame, if you have a gas stove, heat the pan directly. They are touching each other. For something like convection, you can think of an oven. Does anyone here have an air fryer at home? Okay, a couple of you. They seem to be getting more and more popular. An air fryer is basically a heavy-duty convection oven. It's not actually frying anything. It's just using super hot air and the science of convection, in the sense that hot air is going to rise up and circulate rapidly through that oven to make the food cook faster at a higher temperature and create that sensation that you get when you deep fry something. So by definition, convection is a heat transfer through the mixing of parts, of components, but it has a directionality to it. So if we draw ourselves a container here, what we will find is that convection will generally pull things in an upward direction. And then in the case of a convection oven, as the heat gets absorbed toward the top, it falls back to the bottom. Where it gets heated up again and it just kind of circulates. And then finally, radiation. Radiation is the outward transmission of heat in all directions from a hot substance to the surroundings. So we tend to think of it most as this kind of side-to-side heat radiation, because the bottom of a container is going to be touching something else and heat primarily via conduction. Above the container, above the hot object, we're gonna see more convection currents. We tend to think of radiation as kind of a side-to-side thing, but understand, heat radiates in all directions. It's just these other two forces tend to dominate radiation by comparison. Now, when the temperature of a heated object hits about 932 Fahrenheit, the radiation becomes visible. The energy of those infrared packets of light start to creep into the visible light spectrum where we can actually pick them up and see them. Before then, the light, the infrared radiation is just not energetic enough that our eyes can detect it. But once we hit that certain point, we've hit a certain energy threshold where our eyes can see it by then. From a firefighting standpoint, this is a pretty good example of how a fire can spread from floor to floor. We can see that with very few exceptions, fires that are spread in homes rarely are done so through conduction. There just aren't very many conductive materials in a home because other than your pipes and maybe your air ducts, there isn't a whole lot there that actually can get hot enough and is conductive enough to be able to spread a fire from one area to another. In a house or a building fire, convection is by far the much more dangerous proposition because you've got a literal container. You've got a floor above you in the form of a ceiling. And so as that convection current starts to rise, as that heat starts to rise, it hits your ceiling and starts to radiate down. We start to get those convection currents occurring. And if the fire is continuing to rage on the floor, those convection currents continue to manifest, continue to go, and eventually enough heat starts to be generated that the ceiling catches on fire as well and can spread up to the next floor and to the next floor and to the next floor. Which is why when you approach this kind of thing from a firefighting standpoint, firefighters usually start working kind of top down instead of bottom up, because they want to cool down those top layers because of the convection to try to contain the fire before it rages too much out of control. Now, from a radiation standpoint in a house fire, again, not a whole lot of radiation goes on, but if the fire is hot enough, you can see some of those radiation. If it gets hot enough, if the houses are close enough together, which again happens more in larger cities than in towns like this, you do tend to see where adjacent buildings can catch on fire because of the radiative heat that comes on. Then you've got a real problem. We're going to switch gears. Talking about pressure now. So all that stuff previous, that was all about temperature and heat. Now we're going to get into pressure. And so the subject of today, or at least the last 10 minutes of today, and most of Friday is going to be about pressure and gases. And we're going to get into our first hazardous material of the semester in the form of compressed gases and cryogens, as we kind of look over and spill over into Monday, perhaps. Pressure. Pressure is measured via a barometer, and the creation of the barometer is credited largely to Evangelista Torricelli. Evangelista Torricelli is an Italian physicist, and he devises the first thermometer by taking, or the first barometer, by taking this glass tube that is closed on one end, sucks all of the air out of that tube, and then puts it upside down into an open bowl of mercury. And what he finds is that when he does that and there's nothing in the tube, the pressure that is being exerted on the bowl of mercury by the outside air is enough to push mercury up the tube, and he can measure how far it goes up. And so he recognized that there's a relationship between the overall pressure exerted on the outside of the bowl of mercury and how high the mercury climbs up in his tube. Does some calculations of force and area to find the pressure. And so this is a mock-up of kind of the setup that Torricelli used. Now, what's interesting about this particular setup is that there are actually two forces in play here. On one end, we've got the atmospheric pressure pushing down on the pool of mercury, which is in turn pushing the mercury up the tube. But there's another force going on here, a downward force. What is the downward force that is pushing the mercury back down the tube? Gravity. Exactly. And so at some point, the force exerted by the atmosphere equals out the force of gravity, and that's when we can measure the height of the column. And so to that end, what we are able to determine is that in Torricelli's barometer, average atmospheric pressure, sea level atmospheric pressure, is about 760 millimeters of mercury. Now, to us living in the United States, where 760 millimeters doesn't really context to anything. I mean, yeah, it's 76 centimeters, but again, what does that really mean? Well, in PSI terms, it's 14.7 PSI. So, kind of contextualize that to your car. Most car tires require a pressure of somewhere between 32 and 36 PSI. So this would be a little bit more than half of that. So double this and take a couple extra PSI, and that's your tire pressure. So atmospheric pressure is a good thing to kind of know. Atmospheric pressure does a lot of things to give us information to tell us kind of some of the things that are going on around us. What else can we know? What else can we determine out of this? Well, for one, there are lots of different pressure units. In the metric system, the metric unit of pressure is something called the Pascal. I will tell you that even among physicists, pascals are rarely used. They represent a tiny amount of pressure. For example, there are just over 101,000 pascals that represent atmospheric pressure. So even in the metric system, they tend to use kilopascals to describe things like atmospheric pressure. 101.3 kilopascals is normal atmospheric pressure. Here in the United States, we tend to focus on inches of mercury. That's what our barometer readings tend to be. If you watch the weather forecasts, either on the news or you go to your favorite weather app, you'll find that that's how they give you barometric pressures: 29.92 inches of mercury, 30.07 inches of mercury, 28.9 inches of mercury, whatever the case may be. We also use PSI, although that's usually for more commercial kinds of applications. Again, things like tire pressure, gauge pressure for gas cylinders, those kinds of things. The metric equivalent is the millimeters of mercury, sometimes referred to as the torr, as kind of a hat tip to Torricelli and his contributions to the science. All of those items can be made equivalent to each other. So an atmosphere is equal to 29.92 inches, which is equal to 14.7 PSI, which is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101.3 kilopascals. So since all of those values are equivalent to each other, what that means is that any kind of unit conversion could be done to help us convert from one unit to the other. Just like we did earlier in the chapter with converting inches into miles, or meters into feet, or liters into milliliters or cubic centimeters. We can do the same kinds of things here. All right, last tidbit for the day. Barometric pressure is a useful tool for us. I already mentioned weather forecasting. This is the kind of the hidden trick that is associated with what meteorologists do in terms of helping to try to predict weather. one of the things that they look at is not just barometric pressure, although that is somewhat important, but changes in barometric pressure. So generally speaking, when air pressure is higher than normal, that means that the atmosphere is pushing down on us a little bit harder, and that tends to push out humidity, clouds, other kinds of precipitation. We tend to, in the summer, find hot days that are kind of dryish. And in the winter, that means that we get our coldest days that are also usually quite dry. As pressure eases up and we start to go lower, that's what allows the clouds to come back in. In summer months, that means rainstorms, thunderstorms, depending upon, hot air and cold air conditions. That can be things like tornadoes and other stuff. But in general, low pressure tends to mean cloudy, humidity, rain, or in the case of winter, snow, ice, those kinds of things. And so they watch for those differences. As we go from low pressure to high pressure, that usually means that whatever was coming in is starting to go away, fairer weather is coming. As we go from high to low, that usually means that our clear skies are going to get cloudy and we're going to get some kind of weather event. Rain, snow, ice, depends on the season. So that's it for today. On Friday, we will start to look at how we can apply pressure and temperature to describe gases using some things called the gas laws. And then we'll pivot into talking about how we can use temperature and pressure to actually predict phases of matter and use that information to start to talk about cryogenic materials. Have a great day.